How many stars can a planet have? In this video, we will talk about multiple star systems. A multiple star system is a group of two or more gravitationally bound stars. Let's start with the simplest type, the double star system, also designated as a double star, physical double star, or binary system, in which the two components orbit around the common center of mass. If the two stars have a similar mass to an external observer who observes them from a certain distance, the two stars will seem to orbit each other. If, on the other hand, the two stars have very different masses, the less massive star will seem to orbit around the more massive one, because the common center of mass falls within the latter. If there are no tidal effects, no perturbation from other forces, and no mass transfer from one star to another, a binary system is stable, and both stars trace an elliptical orbit around the center of gravity of the system indefinitely. If, on the other hand, the components of a binary system are close enough, narrow binaries, they can reciprocally distort their atmospheres, and in some cases they can even exchange material so as to modify their normal evolution. A variety of narrow binaries are so-called contact binaries, which are so close to each other that they share a considerable percentage of matter. In a binary system, the brightest component is called primary, the less bright secondary. One or both stars may be accompanied by planets. It is important to point out that in addition to the double physics linked gravitationally, there are also double visual stars, which are not physically linked but are located close together only for a perspective effect, and which we will not deal with in the video. Examples of binary systems are Sirius, a binary consisting of a type A star with main sequence and a white dwarf; Procyon, which is similar to Sirius; Mira, a variable consisting of a red giant and a white dwarf; Delta Cephei, a Cepheid variable; Epsilon Aurigae, an eclipsing binary; Spica. Let's now speak of multiple systems formed by three or more gravitationally bound stars. Systems of three stars are called triple or ternary systems. Quadruple systems consist of 4 stars, quintuple systems of 5 stars, and sextuple systems of 6 stars. There are also systems made up of 7 or more stars, but they tend to be unstable due to the complex gravitational interactions between the components. These multiple star systems are much smaller than open star clusters, which typically contain 100 to 1,000 stars. Multiple star systems can be divided into 2 main dynamic classes: hierarchical systems, which are stable, characterized by nested orbits that do not interact much, and thus each level of the hierarchy can be treated as a two-body problem. Trapezia, so called by the name of trapezium in Orion, and characterized by highly interacting unstable orbits. Modeled as an n-body problem, they exhibit chaotic behavior. They can have 2, 3, or 4 stars. Now we deal with hierarchical systems. The first type of hierarchical system is the triple star system, formed by 3 gravitationally linked stars. The 3 stars travel in an elliptical orbit around the common center of mass and are generally arranged so that 2 of the stars form a narrow binary star, while the third star orbits a great distance from the binary on a very wide orbit. This configuration, called hierarchical, is very stable because the narrow binary star can be considered as a single star in the orbit calculation, and therefore the motion of the stars can be described by the two-body problem, which concerns the motion of 2 point-like bodies under the action of Newton's law of universal gravitation, and which are therefore in orbit around the common center of gravity. However, if the orbits of the binary and the single star were comparable, the system could become unstable, and this would lead to the expulsion of one of the 3 stars from the system. Some examples of triple stars are Polaris. The system is composed of a yellow supergiant star of spectral type F7, Polaris, and 2 white yellow dwarf companions of spectral type F, Polaris AB and B. The Rigel-Kentaurus Alpha Centauri system consists of a main pair, consisting of a yellow dwarf, Rigel-Kentaurus A, and an orange dwarf, Rigel-Kentaurus B, around which a red dwarf, Proxima Centauri, orbits at a great distance. HD 188753 is a triple star system located about 149 light-years from Earth in the constellation of Cygnus. The main star, HD 188753a, is a G-type yellow dwarf star with a mass of 1.06 times the solar one. At a distance of about 12 AU, there is another pair of stars that make up component B, which is a spectroscopic binary whose components are called HD 188753ba and 188753bb, respectively an orange dwarf and a red dwarf. These two stars have an overall mass equal to 1.6 times that of the Sun, and an orbit around HD 188753a, or rather around the common center of mass, over a period of 25.6 years. BA and BB, on the other hand, orbit each other in a period of 154.45 days, while their semi-major axes are respectively for BA and BB of 0.28 and 0.37 AU. A special mention deserves the star system of GW Orionis. Until recently, it was believed that there were no planets orbiting three stars at the same time, but a recent study published in monthly notices of the Royal Astronomical Society has overturned this idea. The researchers started from the study of the triple star system GW Orionis, a very young star system formed less than 10 million years ago. GW Orionis consists of a narrow binary whose two stars are just 1 astronomical unit apart, and a third companion 8 astronomical units from the binary. The observations revealed that around the three stars of GW Ori there is a disk of dust that surrounds them all, a circumtriple disk. About a year ago, the telescopes of the ALMA network were able to distinguish 3 dust rings. The first with a radius of 46 astronomical units, the second of 188 astronomical units, and the third of 366 astronomical units. To get an idea, Neptune's orbit is 10 times closer to the Sun, 30 astronomical units, than the last ring of GW Ori's system. But the oddity is another. The disks are not aligned with each other, and there is an empty region within one of them, about 100 AU from the center of mass of the stars. The strangeness of this system actually lies in the presence of a deformed, misaligned protoplanetary disk, literally torn apart by the stars around which it orbits, identified by a team of researchers who use the Very Large Telescope of the European Southern Observatory, VLT of ESO, and the Atacama Large Millimeter Submillimeter Array, ALMA. This is an important discovery because it shows that those exotic planets that form around 2 or more stars, in this case we always refer to the planet Tatooine from Star Wars to immediately understand what we are talking about, can in fact be born in inclined rings and bent disks precisely because of the strong gravity that the stars can imprint. Unlike our solar system, where the planets are more or less all on the same plane of inclination, in other star systems this may not be the case, and this can happen especially in those systems where there are 2 or more stars. Another peculiarity is that the 3 stars of GW Orionis do not orbit on the same plane, but are misaligned with each other and also with respect to the disk. Precisely this misalignment would have caused the rupture of the protoplanetary disk. Multiple star systems with 4 or more stars can give rise to very complex configurations. These configurations were studied in 1968 by David S. Evans using the pendant diagrams, so-called because they recall certain decorations that hang from the ceiling. Each level of the diagram shows the decomposition of the system into 1 or more smaller stellar subsystems. Each pendant in the diagram represents a subsystem, and in turn can be formed by 2 stars, or by a star and a smaller subsystem. Each of these subsystems can in turn have a hierarchical structure, which means that they in turn must be divided into even smaller subgroups, and so on. Each level of the hierarchy can be treated as a 2-body problem, considering the stars of a binary pair as if they were a single star. In these systems, stars follow stable Keplerian orbits around the center of mass. Some examples of multiple star systems with 4 or more stars are: Capella is a multiple system consisting of 4 components grouped into 2 binary stars. The first pair, which constitutes the predominant element of the system, is formed by 2 giant stars of spectral class G, both having a mass of about 2.5 solar masses and a radius that is around 10 times that of our star. The two stars which orbit around the common center of gravity, following a rather narrow trajectory, are in a rather advanced phase of their evolution. The secondary is preparing to become a red giant, while the primary is in the phase of helium fusion. The other couple is away 10,000 astronomical units from the first and is composed of two faint main sequence red dwarf stars. The star V1054 Ophiuchi Gliese 643 is a system made up of 5 stars divided as follows. The narrow binary formed by the two red dwarf stars V1054 Ophiuchi BA and V1054 Ophiuchi BB, and the red dwarf star V1054 Ophiuchi A orbit around the common center of gravity, thus forming a triple star system. Also present in the system are the star Gliese 643 and the star V1054 Ophiuchi C. Castor, or Alpha Geminorum, formed by 6 components arranged in 3 different pairs. The first two, Castor A and Castor B, are 2 spectroscopic binaries belonging to the first subclasses of spectral class A, separated from each other by 4.8 seconds of arc. Castor A and Castor B orbit around the common center of gravity. The third pair, Castor C or YY Geminorum, is formed by 2 red dwarfs and is separated from the first 2 by about 70 arc seconds. Trapezius systems are usually very young and unstable star systems. It is believed that they form in star-forming regions within the nebulae, and that they tend to fragment into stable systems, expelling some of the components. These systems take their name from the trapezium cluster in the heart of the Orion Nebula and represent a fairly widespread type present near or within nebulae. Finally, let us mention the designation of multiple star systems. The components of multiple stars can be named by adding the suffixes A, B, C, etc. to the system name. Suffixes such as AB can be used to denote the pair formed by A and B, the sequence of letters B, C, etc. It is usually assigned based on the separation from the component. Components discovered near components already observed may receive the suffixes AA, BA, and so on. The multiple star catalog of A.A. Toko-Vainen uses a notation system in which each subsystem in the pendant diagram is designated by a sequence of digits. For example, in diagram of the figure below, the larger system receives the number 1, while the subsystem containing the primary receives the number 11, and the one containing the secondary receives the number 12. The subsystems contained in the 2 largest receive numbers of 3, 4, or more digits. When this method of notation is used to describe non-hierarchical systems, the same number is used to designate multiple subsystems. For example, a system with 3 visual components, A, B, and C, neither of which can be grouped into subsystems, will have 2 subsystems designated by the number 1, the binaries A, B, and AC. If components B and C were to turn out to be binaries, they would receive the numbers 12 and 13. Be sure to join the channel, leave us a like, and click on the bell. You will help us to make products of even higher quality.